Alright everybody, what's going on? This is Mr. Diamond, and today what we're going to be doing is I'm going to be going over a couple of questions from the physics worksheets. In class I may have other examples that I dig up and I find and use, but I wanted to try to go over a couple of examples and try to explain my full thought process as I go through the entire worksheet and I answer every one of the questions. Now the example problems I'm going to do is on worksheet 3.3. I'm going to do number 2 and number 3. And on worksheet 3.4, I'm going to do example number 4. And again, I'm going to try to talk through my full thought process as best I can as I'm going through the entire problem. So we're going to start with number 2 and number 3, which are related to each other on worksheet 3.3. And the question says a 20 kilogram box is resting on a table the first question, or this would I guess technically be number 2, not letter A, but number 2 is what is the weight of the box and the normal force acting on it. And then number 3 asks, we're going to take that same 20.0 kilogram box, and it wants to know what is the force of gravity and the normal force, but with a 10.0 kilogram box on top. Okay, so all the problems that I do, even though you were kind of able to avoid having to do it in earlier problems on this class, we are at the point where you basically have to draw a picture every time. So we're going to start. I'm going to go ahead and work on number 2. I was going to say letter 2 and then number A. So I've got a box. I like to write the 20.0 kilograms in my box, just so I remember that's the thing I'm talking about. And it's resting on a table. So I'm going to also indicate that it is on a flat surface. Now, I then want to go through and I want to think about everything that's acting on or is happening to this box. First thing that I think of, the first thing that comes to mind is every single thing that is on this planet, and because the question does not imply that it's not on this planet, is going to be subjected to gravity. So I'm going to go ahead and I'm going to write my FG, my force of gravity. I then ask myself, is the box moving? Well, no. The box is resting. It's simply sitting upon this table. And if it's staying stationary upon this table and it's not moving, that means that there cannot be, because it's at rest, resting, not moving, or a constant velocity, means that the sum of the forces in that direction is equal to 0. Now, the question does not indicate that this box is moving up or that this box is moving down, which means there needs to be some kind of force counteracting the force of gravity that is supporting it on this table. We call that supporting force the normal force. The normal force is the force of the table pushing back upwards on this box, preventing it from falling through or breaking or passing straight through the table. It's supporting it. I then ask myself, is there anything moving in this direction on there? Is there any in the X direction that I need to worry about? And the answer to that question is no. It does not imply that it's being pushed. It isn't sliding. It isn't moving. It isn't on a slope. It isn't doing anything like that. So there's no friction, although there could be friction at play if it was getting pushed. There would be static and there would be kinetic friction. The question doesn't mention that it's moving. Friction only shows up if something is attempting to being moved or if there is a force being exerted in the direction parallel to the surface that it's resting upon. So that's it. That's my 2 forces. And I know that the sum of these forces has to be 0. And so this is for number 2 here. The sum of these forces has to be equal to 0. And so of these 2 forces, I know how to find one of them, and I can use that to find the other one. Force of gravity is always equal to mass times g, which is 9.8 meters per second squared. So I'm going to go ahead and take my 20.0, multiply that by 9.8, and it is going to be down in this problem, so I'm going to go ahead and multiply it by a negative 9.8. A lot of the examples that I've worked out, I've gone back and retroactively added the negative at the end. You could add it in at the beginning, you could add it in at the end, as long as you know that, for example, this is going downwards, so it is actually negative. So I'm going to go ahead and multiply this out. I get 196, or negative 196 newtons, because that's the force of gravity. Okay, well now I know that the sum of my forces in the y direction is equal to 0, which I had up here. I also know that the only things going on in the y direction are the force in the normal direction, or the normal force, and the force of gravity. Which means if I rearrange this, the normal force is equal to the negative force of gravity. So force of gravity is negative 196, so negative 196 newtons is 196 newtons. So this is my gravity, that's my weight, and this is my normal force. Now, the next section of this, notice this one's negative, this one's positive because gravity is pulling down, normal force is pushing up. The next part of this question is going to take this same box, so I'm going to go ahead and draw my same box again. But just like in our bucket example, we actually have a second box resting on top of it. So I'm going to make it smaller and I'm going to make it quite a bit above it. So this box is actually resting upon here. This one is 20 kilograms and this one is 10 kilograms. So I'm going to make it a little tiny 10. And I'm going to go ahead and box off this section here. So we're now in number 3 territory. We're in question number 3. So both of these boxes are interacting with each other. And what I mean by that is because this is coming into contact with it in a way where there's actually going to be force directed upon it, i.e. weight, it's going to have some effect on this lower box, and this lower box is going to have some effect on this upper box. An example on worksheet 3.4, number 4, there is going to be some where we don't have that, even though they're in the contact. That's usually when things are horizontal, like if I hold my hands together but I'm not actually applying force, if I just kind of barely let my fingertips rest on each other, there's not actually any, there's a little bit of friction, but it's not being pushed up against, or it's not being attempted to be moved in that direction, so we don't really care about that friction. It's more when things are going downwards, because if you're dragging, you've got gravity pulling you down, making it harder to move something across the surface. So both of these are going to have gravity. It sounded like from the emails and the conversations we had that everybody's feeling pretty good about gravity. It's really when the other stuff starts showing up that people start having a little bit of issues. And I might be doing another example in addition to this. I've been looking through the worksheets and trying to find another good one. I'll see if I have time after I'm doing this, how I'm feeling at the end of this video, if we'll do that or make that a separate video. Now, I mentioned on the bucket example on question number 4 on this worksheet that it's always best to start at the thing that has the least forces going on with it. So this box here is being affected by gravity, normal force from the table, and also this box. And this box is being affected by gravity, and it's got to be being affected by a normal force. Now, how do we know it's being affected by a normal force? Well, it's resting on top of something. It's saying that this box is resting, if we look back at the question, the same box as number 2, but with a 10 kilogram box resting on top of it. So this box is also not moving. That means there's no forces in either of these directions. There's no friction, there's no push, there's no pull, anything like that. So all we've got is the normal force supporting it and the force of gravity going upwards. Now I'm going to call this normal force 1 because that normal force has to come from somewhere. It's one of Newton's laws. All of our forces have to have an equal and opposite reaction. They have to cancel each other out. It has to come from somewhere. So this normal force 1 is actually going to come from this box here. So this box here is exerting, it's pushing up with a certain amount of force on this box. And this box here, to cancel that out, the equal and opposite force is actually going to have to go down on this box. Now I'm going to go ahead and make this G G1 and this G2 as well, just to keep them straight. And then here, there's going to have to be a normal force, but that normal force is going to be accounting for the gravity and is going to also have to cancel out the weight that this box is pushing on this box. So we're going to call that Fn2. So we've got all of our forces. There's no movement. It's at rest. It's resting on the table, and it's got a 10 kilogram box. If you look back at the original question, it says resting on top. There's no movement in the x direction. Everything's in the y direction. And because there's no movement in the y direction, we know that the sum of our forces in the y direction has got to be equal to 0. It does not mention any movement at all in relation to these boxes. So let's start with some of the forces for box number, or we'll do y and then box number. Sorry about that. That sneeze. For box number 1. Well, in this case, we've got force in the normal 1 plus force of gravity for the top box. And both of these must be equal to 0 because there is no movement of this box. Force of gravity, we already have an equation for that. Force of gravity is equal to mass times gravity. Mass of this box is 10. Gravity is negative 9.8. 98 newtons is going to be our gravitational force. So if we rearrange that, we will get normal force is equal to the negative force of gravity. Just like last time, it's going to be set up the exact same way. Negative force of gravity is going to be negative 98. Our negatives will cancel out, and we're left with 98 newtons. Now, the reason we needed to know all this information, even though it technically asks about the second box, is we needed to know this force here, and to do that force, we needed this force here. And the reason for that is, again, this normal force has to come from somewhere. Here, when we did this first example up here, our normal force was coming from the table. So if we were to actually be like looking at this and thinking about, okay, well, what about forces acting on the table is actually being pushed down, or is getting kind of the weight force, or the normal force is going to be coming from this table here. And it's going to also have a magnitude of 196 newtons downwards. And this makes sense because when you place an object on a table, it adds that weight if you were to weigh the table. That table has to support itself plus whatever else is upon it. So now we know that this is the weight, or the normal force that is being exerted on this. It has to come from somewhere. So to cancel out this upwards, it has to be the equal and opposite. It has to be going downwards. And again, notice they're exerted on opposite things. So now, if I go sum of the forces I'm going to draw my y better, but now we're going to do 2. I've got force of gravity 2 plus normal force 2 plus, now I've also got the normal force that it exerted on that top box. So force of gravity, we already have. We solved for it up here. Force of gravity is going to be 196 newtons. We also know that all of this is going to be equal to 0. So we're going to get equals, force of gravity up here is negative 196 newtons plus whatever the normal force is, plus, and this is going to be another negative because now it's the opposite direction as it was earlier, so now it's going to be negative 98. So this all equals is 0. So I'm going to move that over here. So if I add 196 and if I add 98, I'll get the normal force 2 is equal to 294 newtons. And I did skip a small step in here. I skipped gravity, but because the gravity of the box by itself has not changed, the weight of the box has not changed, we could just pull this number right up here. It would have just been 20.0 times negative 9.8. That's the weight of the box. That box also has to support an extra 98 newtons of force that's coming from this box weighing down upon it. So the normal force the table will have to exert on this bottom box is 294 newtons. Basically, this box this table has to exert enough force on this box to support both of the boxes. Otherwise, it would fall through. Okay. Hopefully that makes sense, and hopefully you kind of see where we were going from there. So now I'm going to switch over. I'm going to flip this over. And we're going to do question number 4 on worksheet 3.4. And this is a big multi-part question, but it kind of helps with a lot of the stuff that we have question-wise. Because it gives you basically every single type of problem you could run into. So we've got a box, and that box is going to be sitting in a corner, like so. There we go. And then the question says, list all forces and motion, if any. There might not be, but if any, in each of the scenarios. Assume that the coefficient of static friction is equal to 0.7 and the coefficient of kinetic friction is equal to 0.55. Take a drink real quick. Okay, we know the box is 15 kilograms. Scenario number A. Someone pushes down with a force equal to 100 newtons. So in every one of these scenarios, I'm going to write a table of this information, or I'm going to draw a free body diagram, and one piece of information is going to stay constant, and that is going to be Fg. The force of gravity acting on this box is always going to be constant, so I want to work that out ahead of time because it's just going to make it way more convenient. Force of gravity is always equal to mass times gravity. Mass in this case is 15 times 9.8 equals, it's going to be, we'll call that negative 9.8 for our convenience, negative 147 newtons. So anytime I see Fg in this problem, because it's a big long one, it's got like 6 parts to it. Since the box is staying constant, I'm always going to use this negative 147 as my force of gravity. Okay, so starting with a letter A, we've got my box. Is the box moving? Well, we don't know yet, so let's think about based on what we've got here. First of all, it's always got gravity, so I've got Fg. Someone's pushing downwards, so I'm going to go ahead and draw another arrow here. I'm going to call that one Fp for force of the push. And then because it's being pushed on the ground is going to give a supporting force that's going to prevent it from moving, and this is not going to be to scale. We're going to go have an Fn. Now, you can test this at home. If you take basically any object and you press on it while it's on a table, you can think of it with the pen, that object is not going to move. It's being directed downwards. So, because it's being directed downwards, and notice that it is drawn in contact with this wall over here, but if there's no force pushing it into that wall, there's not really anything that we have to actually really care about. As long as it's just touching, but if it's not actually being pushed against it, you don't have to count anything that's coming from that direction. Okay, so let's go ahead and in the whole system here, if you're pushing down, you would expect it to not move, which means the sum of the forces is going to be equal to 0 because you're just pushing down on an object. So what we need to do now is say, well, I've got normal force, I've got force of gravity, and I've got the force of a push. We know 2 of these values. We don't know normal force. We know that gravity is directed downwards, so that's a negative 147. And we know that the push is also directed downwards, so that's a negative 100 newtons. So if we plus these to both sides, we can get that our normal force is equal to 247 newtons. Gravity is 147 newtons. And I'm going to make it negative because it's going downwards. And then the force of the push is equal to 100 newtons negative because it's pointing downwards. Okay, that is the first example problem that we've got to deal with. Second example problem. Okay, now we've got the box. And we've still got our same box as before. There's still gravity going downwards, but now we're going to be pulling up. So if you're attempting to lift something, or if something is lifting or is moving upwards or has a force upwards directed upon it, the first thing you want to check is you want to check if it's enough to overcome gravity. Because to lift an object, all you're doing is you're overcoming the weight of that object, and the weight is equal to the mass times gravity. So what you need to figure out is the force being exerted higher than Fg? That's how you decide if something is being lifted upwards. And in this case, 147, it's negative because it's going downwards. You'd have to have something greater than 147 positive newtons force upwards to allow something to be lifted. Since this does not meet that threshold, since this does not meet that criteria, we know that it's actually going to stay on the ground. And because we know it's going to stay on the ground, it means we're also going to have the normal force. Now, again, your instincts might tell you that, okay, well, can I just pull this normal force from here? But no, because the normal force changes. It changes based on how much pressure is being applied. If you were to just look at this as the box was sitting by itself, 15 kilograms by itself, it would have a normal force of 147. Pushing down increased that normal force. Pulling up is going to decrease it, because the more upwards force you add to something, the less the thing that it's sitting on has to support it. And the normal force will drop because of that. So we're still not going to have any movement because we've checked to see if this is bigger than the force of gravity, and it's not. So sum of the forces equal to 0. We've got force, normal, force of gravity, and then force, again, I'm going to use P for push or pull. Now we can list them out. Normal force, we don't know yet. Force of gravity we've got from up here, that's negative 147 newtons. And this time the pull is going upwards, so it's going to be a positive 100 newtons. And then the only thing we've got left after that is the normal force. If we rearrange, if we combine terms and move them over there, we will get positive 47 newtons equals the normal force. And then force of gravity is the same. It's still going to be our negative 147. And then just for thoroughness, our push, or our pull, in this case it's a push, is going to be positive 100 newtons. And all we did here was we rearranged this. 0 equals negative 147 plus 100 plus force normal. Okay, let's get that out of the way. Let's go to letter C. For letter C, someone pushes against the wall with a force. So this one's really interesting because, first of all, we haven't actually talked about any examples like this. But the key idea here is we're still going to have force of gravity. And we're still going to have the normal force because we're not changing anything about that direction. So it's not like you can't push on something sideways and it's just going to go upwards unless there's way more complicated stuff like aerodynamics and lift and all that garbage involved. We're going to be pushing, and based on my picture, we're going to be pushing this direction. And that's going to kind of make us have to figure out, well, then what's going to happen here? If it's on the wall, pushing it will not move it. Again, we'd have to be pushing it through the wall. That's going to involve way more complicated, way more stuff than we actually are dealing with in this class. So that means the wall must actually be pushing back on the box. It must also be, when you push on something against a wall, the wall is going to push back on the object. And so because of that, because the push is going to go right up against this wall, we're actually going to have a second normal force. This is going to be the normal force coming from the wall. So I'm going to call this normal in the y direction and this normal in the x direction. And they're each going to be distinct from each other, but we still call it normal force. It's still the force that's opposite of the direction that it's being exerted. It's just weird to think about the fact that it's coming sideways, but it is still a normal force. It's still an object pushing back after it's being pushed upon. But we're going to have to solve them separately, and logic should tell you that if you push sideways against this box that's on this wall here, it's not going to move. And because of that, we also don't really have to care about friction because, again, it's not moving sideways. It's just going to be staying in place going up against the wall. So we can go ahead and say, well, the forces in the y direction is equal to 0. The forces in the x direction also equal to 0. In the y direction, we have Fg, and we have the normal force. In the x direction, we have normal force in the y direction, sorry. And then we have the force of the push, and then we have the normal force in the x direction. Now, each of these, we have one piece of information. For force of gravity in the first one, we've got negative 147 plus force normal in the y direction. And then for this one, we have a positive push. Again, it's actually going to the left, so I'm going to make that negative of negative 100 newtons plus force normal x. And so for both of these, we're going to plus 100 plus 147. The other side is 0. Force normal y is equal to 147 newtons, and force normal x is going to be equal to 100 newtons. So the wall is going to be contributing 100 newtons of force to the right, preventing the box from sliding through the wall. And the normal force in the y direction is coming from the floor, and the floor is offering 147 newtons of support to that box. Now, because there's no attempts to actually be moving that's not going a direction that could cause it to move, we don't actually have to care about friction. The next example, however, in example D, we are going to have to actually start caring about friction. So I'm going to go ahead and draw my box, good old friend. And now this time we're going to be pulling it away from the wall with our force of our pull. Now again, does not mention anything in the x or in the y direction, which means we're going to have the normal force and we're going to have gravity. This time, those are a little bit more important though. Oh, sorry everybody for my yawn. Because since we're going to be trying to move it away from the wall, now, and you've probably noticed by now, I like to draw it down here closer to the floor. We're going to have the force of friction. Friction is going to attempt to move it. So, because friction is involved, it's involved because this is a process that could actually result in moving. Pushing something against a wall, you don't need to consider friction on the floor because it's not actually trying to slide it anyway. It's just adding pressure to something. It's the same way as pushing against a wall. You don't actually have to care about the friction of your body in that case. Okay, so what we're going to do next is, well, we can get our Fg and we can get our Fn. That's a pretty straightforward first step. Force in the y direction is equal to normal force plus force of gravity, and we know it's not moving in the y direction, so that whole thing has to be combined together to 0. We know that Fg is negative 147, and we know that that means that our normal force is equal to positive 147 newtons. Now, once we have that piece of information, because friction is involved, we first need to check if it's moving. And so to do that, we need to calculate the force of static friction max. And what I haven't used that actual as a phrase here yet, but remember, static friction increases and increases and increases until it's overcome by whatever force you're adding, and then once that happens, an object begins to move, and you care about kinetic friction. So what we're saying here is you need to figure out how much will it increase to before you go over and the object actually starts moving. And the force of static friction max is, again, I haven't used that exact language, but it's literally just coefficient of static friction times mass. Like that is it. That's what that equals right there. So we're going to plug that in. Coefficient of static friction is 0.7 times the mass is going to be 15. 0.7 times 15 equals, I believe, that's not correct what I have written down there. Let me dig out my calculator just to make sure that I have the right numbers. Blah, 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 blah. Okay, 0.7 times 15 is 10.5. Oh, sorry. That's why I made my mistake there. You guys probably caught me. Normal force, not mass. I apologize, everybody. It's been a long year at this point. Okay. That's why my number looks so wrong anyway. So, normal force. And again, the reason it needs to be the normal force, really apologize that I messed this up the first time. It needs to be the normal force is because the normal force is how much the table is pushing back up on something. The more it's pushing back up, the harder it's going to be to move it. That's also why lifting an object slightly will make it easier for it to slide across a surface. So our normal force in this case is the normal force that we used right here, which is 147. We multiply that by 0.7. That's the number that I had on my key earlier. So what this number will give you is the force of friction static max is equal to 102.9 newtons. Again, apologize for this. Hopefully you feel like you understand why I had to correct it and where we got here. Once you get here, though, we should be good. What this number means is that as you push and push and push and push, so I've got a Mountain Dew right here. As you push and increase and increase and increase your force that you're pushing upon this can, it's going to continue pushing backwards on your finger. It's going to prevent you from moving it because of its friction until you reach this maximum force of static friction. So in this case, as I push and push and push and push and push, nothing's happening. But as soon as I get to that threshold, that's the maximum static friction it can exert, and I've overcome it, and it starts moving, and that's when you switch over to kinetic friction. So any force, this or lower, will not move. It will not move the object. So I first need to ask myself, does this 100 newtons of pull overcome this 102.9 newtons? In this case, no. So there will be no motion. 100 is less than 102.9. So because of that, static friction is not actually going to be equal to this number. This is why I did this max piece right here. Because in the y direction, we know normal force is this, gravity is that. In the x direction, we've now got force of static friction plus force of the pull. And we know that has to be equal to 0. We know the pull, it's going to the right, so I'm going to call that 100 newtons plus force of static friction. Notice it's not going to be equal to this 102.9. If I move this, rearrange this, I'll get my static friction is 100. So why is it different than my max static friction? Well, because the pull wasn't enough. Remember, static friction increases its pull or increases how much force it has as you apply more and more force to it. And if you think about it, this makes sense, because if this was 102.9, that would mean that once you pushed on an object, like if I pushed on this, let's say I have my calculator here, if I pushed on it with less than the force to overcome static friction, if it was always that maximum amount, when I pushed, my calculator would just, as I push from this direction, start going backwards, because static friction would literally be shifting it backwards against me. That's not how it works. Static friction builds and builds and builds as you add more and more and more and more force to it. You can almost think of it like, I don't think I've done this explanation ever, but this might help make sense. It's kind of like a 1-to-1 ratio on the graph of static versus push or pull. And it'll be 1-to-1, 1-to-1, 1-to-1. So if you put 10 newtons of push force, static will do 10 newtons. 30 newtons, 30 newtons. 50 newtons, 50 newtons. But then eventually there's a point where static friction just stops. And that stopping point means that as you increase and as you go further this direction, it doesn't matter what this number is. You've hit that threshold. This graph physically won't go any higher. Your push and your pull force can keep going, but static friction will not keep going up. This is its maximum point, is this right here. This would be max. And so here what we're saying is we've only pushed 100 newtons of force. We've only landed at this point of the graph. We've only made it to that level, so we just pick that number. Whatever was added by the push or the pull, that's what we had. And then up here is where you would use kinetic force. You'd switch to whatever kinetic friction was. Maybe those of you who are more graphically inclined, that'll make more sense to you and kind of help you logically figure out what it's talking about. Okay, so we know force of static friction is 100 newtons, and that means that the force of the push, in this case, is also 100 newtons. Okay, let's go ahead and do example E. So now it's going to be the same setup, so we can steal a lot of our information here. As you probably noticed, we can steal a lot of the information from a lot of these questions. But now our pull is going to be bigger. So we've got our FP, we've got our FN, we've got our FG. I know I'm kind of skipping over those pieces, but I really hope that you're feeling like you understand where those are coming from at this point. So now what we're going to do is, while we're pulling, that means we're going to have friction. Friction is going to be at play yet again. Notice it's set up exactly the same ways here. I've just drawn the push or the pull a little bit bigger. Not really. It's actually just shifted over one. I was going to try to make it bigger, but I guess I didn't. So we're going to steal from D that Fg is equal to negative 147 and normal force is equal to 147. So we did the exact same calculation up here. We've got that same information. Now we do the same check, but 200 is bigger than 102.9, meaning there is motion. And that means we use the coefficient of kinetic friction. So what you do if this was an independent problem is you would do what we did up here. You would say, okay, I know the normal force is 147. The coefficient of static friction is 0.7. 0.7 times 147 is 102.9 newtons, which means just like before, if you keep going and going and going up here, the point at which static friction can go to the max is 102.9 newtons. Anything beyond that point up here, you've got to use kinetic friction because the object is actually moving. That's the maximum that it can use to resist it. Since 200 is bigger than this, 200 is up here, you're now in the realm of kinetic friction. You're now in the realm where kinetic friction will take over, and that means that there will be motion. And so that means, in addition, that the sum of the forces in the x direction does not equal 0. That means you are actually going to have some sort of motion in this direction. So what we're going to have to do first is we're going to have to actually solve for all of our pieces. So what do we have in this direction? Well, we're going to have force of the pull, which is going to be 200 newtons. And then we're going to have the force of kinetic friction, of Fk, or I guess I should do Kf, so you're less likely to put your brains in the gutter that that's meaning a word you shouldn't be using. And in this case, that's going to be equal to the normal force times mu k. I know I've flipped the order, but it's the same type of calculation up here. It's just now we're using kinetic friction. So this will, when you plug it in, I can do that really quick. So up at the very top, we said kinetic friction is smaller than static friction. Kinetic friction is 0.55 times our normal force, which is 147. We get 80.85 newtons. So now I've listed all my forces. I have Fg, I have Fn, I have the push or the pull, and then I have that friction is going to resist with a force of 80.85 newtons backwards. Again, I know that it's moving and it gives me the coefficients, so it has to be a friction, it can't be a frictionless surface, so there has to be the object is going to resist moving along that because of friction. Anytime an object, unless it specifically says that it's frictionless or it gives you no coefficients to work with, or it tells you that you need to assume that, anytime an object is moving horizontally, there's got to be friction at play. So we did the check. We checked to make sure, okay, static friction's maximum is 102.9. This exceeds that, so friction is going to be exerted, but it's going to be kinetic friction, and the object is going to be moving. So what we're going to do now is we're going to say the sum of the forces in the x direction is equal to FKF plus FP. That means it's going to be equal to 200 minus 80.85. I'll rewrite it down here. 200 minus 80.85, which will be equal to 119.5 or 0.15. So now this 119 is equal to the sum of the forces. And we also know, based on Newton's laws, that the sum of the forces is equal to ma. Now we haven't directly used this equation a bunch, but this equation, the F equals ma, is the reason we have made on all of these questions the assumption of 0, 0, 0, 0. All of those zeros come from the fact that if something is not moving or accelerating, anything that's not moving or accelerating means that A equals 0, means that F equals ma equals 0. I don't actually think I explicitly laid that out in the earlier ones, but this is why we get to make this assumption and this assumption and this assumption right here, because it's not moving. If it's staying still, acceleration has to be 0, which means that F equals ma has to be 0, which means the sum of everything together also has to be 0. But in this question, it is moving. It does have an acceleration. So we can actually take this number and we can plug this in. Instead of assuming a is 0, we're actually going to have to solve for acceleration. So m in this case is going to be 15. So acceleration is going to be 119.15 divided by 15. And when you plug that in, you get 7.943333 or 7.94. That's an acceleration. So it's meters per second squared. So if you pull on this box with a continuous force of 200 newtons and you keep pulling, it will begin accelerating faster and faster and faster at a rate of 7.94 meters per second squared. Okay, closing in. I'm going to flip actually back to the first page because I have a little bit of space on there. We can do F. This will definitely be the last example I've got on here. This video is closing in on 50 minutes. So we've got F. So same box, good old boxy friend. We've got gravity. We've got normal force. But then this one time it says it's being pulled away from the wall at an angle of, so I'm going to go upwards at an angle of 28 degrees with a force of 200 newtons. And because it's being pulled this direction, there's also going to have to be friction at play. Again, the whole point of friction is that if anything is trying to move it doesn't have to be moving itself, but if it's trying to move it in a direction other than up and down, if it's trying to slide it down or up a horizontal, or up a slope, or if it's trying to slide it left or right on a horizontal or on a surface, you've got to account for friction, because that's either going to be preventing it from moving altogether if it's static friction, or it's going to be making it harder to move, and it's going to be reducing how much it moves by if it's kinetic friction. Now, in this case, what we're probably going to want to do is we're actually going to want to split this. We're going to have some of the pull being in the y direction, and it's actually going to be lifting it upwards and reducing the normal force required to support this. And then whatever is left over is actually going to be the pull in the x direction that's actually going to be moving it forward. So I'm going to first take my slope. I've got 28 degrees. I know this is 200 newtons. We're going to use our resources and our abilities from previous chapters to solve for what our other pieces are. In the case of y is equal to 200 times sine of 28. And x is going to be 200 times the cosine of 28. Now, the reason for this is, again, if I got a couple colored pens over here. I think we can do that a little bit there. Okay, so in this case, we want the x direction. If we want this horizontal component here, that's going to be adjacent hypotenuse in the angle, so that's cosine. This is opposite hypotenuse, so that's sine. And then we are using the 200 as our hypotenuse, 28 is our angle. So this red here, this x direction here, is going to be the pull that's being exerted horizontally. This in the y direction is going to be the lift that's exerted, that's pulling upwards on the box, which is going to help because it's going to reduce the normal force, because it's going to then, or in doing that, is going to reduce how much friction is being exerted on the box. So let's go ahead and solve these two. I believe when I worked them out ahead of time, I got 93.8943, and then it'll be in newtons. And then I got 176.5895 newtons. Okay, so first we need to figure out everything in the y direction, some of the forces in the y direction. First question we ask ourselves, does this y force, this force right here, overcome the force of gravity? Well, based on what we had back here, we know that our force of gravity from our question was 147 newtons. So let me go ahead and do that. Fg equals negative 147 newtons. So in the y direction, this is not enough to lift the box up. If it was, this question would be a jerk, and it would be making you think you have to do a whole lot of work that you don't actually have to do. Thankfully, this question does not actually do that. I know it would be really frustrating for some of you if that was what the question was doing. But just like we did in the earlier question, we have to check, is this enough force to lift the box? No, it's not enough. This is only 93.8943 newtons. That's not enough to overcome the 147 newtons of gravity. Okay, so if that's the case, then some of the forces in the y direction must be equal to 0, because it's not going to be lifting it. Must be equal to the normal force plus the force of gravity plus the force of the push or of the pull coming in the y direction. So now if we set all the stuff that we know that gravity is negative 147. We know that our pull is going to be going upwards, so that's 93.8943. And then both of those added together plus the normal force will equal 0. So I'm going to add this over here, subtract 93.89 away from that, or 8943 away from that, and you will get, if I have my math correct there, that looks correct. The normal force is equal to 53.105-ish newtons. I did work this out ahead of time. I'm looking at my key to just double check. So again, to go back here and to kind of re-explain some of this stuff here, in this direction here, the box is still not necessarily going to move. We're not guaranteed that it's going to stay stationary. We're not guaranteed it's going to move. So first we need to split this pull apart and see what is it doing in the upwards and what is it doing in the horizontal. In the up direction, or in the y direction, it's lifting upwards with 93 newtons. That's not enough to overcome gravity, so that means that the whole thing must be 0, because the whole sum of the forces must be 0, because if it's not enough to overcome gravity, it's not going to lift the box. If it's not lifting the box isn't accelerating in the vertical direction. If it's not accelerating in the vertical direction, F equals ma equals 0, so the sum of the forces equals 0. So then we've got normal force, gravity, and the force of the pull. Gravity we know is 147, negative, because it's going downwards. 93.8943, that's the upwards pull. Whatever's left over, the table is only actually having to exert 53.105 newtons of normal force upwards to support the box. It's only having to keep it supported by that much. And that's going to be relevant because when we go to the next step, it's actually going to change the friction value because, again, normal force gets used for friction. So then we're going to have to ask ourselves, okay, first, just like last time, check what the force of static friction max is. We need to do a quick check of what that is. So to do that, we're going to take coefficient of static friction times the normal force, write it correctly this time. That will give you 53.105. See, 53.105 times static friction is 0.7. We get a measly value of 37.1735. Which we have blown out of the water. So we are definitely moving because 176 is greater than 37.1735. So since this is definitely bigger than our maximum coefficient of static friction, if you just think of that graph thingy from the last example here, we have hit our maximum. We're now in the realm where we care about kinetic friction. But notice that it changed because back here, the static friction maximum value was 102.9, but because we're lifting upwards on the box, we're reducing the normal force. We're making it so that way the surface does not need to be in nearly as much contact as it was before, and that's reducing the friction, and it's going to mean that you're actually getting less interaction between the surfaces of those materials. So that means, so some of the forces in the y direction, or in the x direction, my bad, x direction, is going to not be equal to 0 and is going to equal force of friction plus, or in this case is going to be kinetic friction, plus force of the pull in the x direction. Kinetic friction, we're going to have to go ahead and take the mu k times Fn. So that'll be Fpx. And if we plug in those numbers from what we've got here, normal force is 53, and our kinetic friction coefficient is 0.55. It's 53.105 plus, and then our force from our normal, our force from our pull. So I guess I'm going to back up because, again, I'm trying to make sure I explain my full thought process here. I know it's moving. The amount of friction that's going to be resisting that movement is the coefficient of kinetic friction times normal force. Normal force we got here was 53.105. Plug that in, and then it's going to be added to, technically this will be going to the left, so it'll be negative. And then the coefficient, or the movement in the x direction from the pull is that number we calculated right there, 176.5895. So we're going to plug all of this in. Sum of the forces in the x direction is equal to, make sure I got my number right here. I got 146.79. I'm going to plug that in just because I have a little bit of doubt about my past self, which I'm sure we can all relate to. 0.105, that's negative, plus 176.5895. 5895, yep. 147. Aha! It is slightly different than I think I was rounding numbers in my example, so it was close. But I'm gonna try to stick with this one unrounded or slightly less rounded number. 147.38175. Now that's the the max or the sum of all of the forces, which as we said here is not equal to 0, which means all of this is equal to the mass times acceleration. We know the mass, because just like always, the mass in this problem has been 15 times the acceleration. So let's divide that by 15. We'll take my number here, divide that by 15, and we will get an acceleration of 9.82545, or 9.83 meters per second squared. So what are all the forces acting upon it in example F? There is the force of gravity that's going downwards at 147. There's the normal force, which is going upwards at 53.105, because there is also an x direction pull that's going upwards with 93.8943 to make up the rest of this 147 newtons, meaning that everything in the y direction cancels out. In the x direction, there's a pull, which we can double check and just make sure that that pull is enough to overcome static friction, just like we would check to make sure that this 93 is not enough to overcome the force of gravity, which it wasn't. This time it was enough to overcome the force of static friction, though, which means that there was definite motion. And so the sum of our forces in the x direction, because there is motion, will not be equal to 0. And then we can set that up to be equal to kinetic friction plus the pull in the x direction. Kinetic friction is equal to the coefficient of kinetic friction times the normal force plus whatever that pull is. Get this value here. It's got to be negative because it's moving to the left in our example here. And then add 176 to that. You get a total of positive 147.38175 as your total force. And so this would be newtons. And then that total force equals the mass times acceleration, which if the mass is 15 means that it is accelerating at 9.83 meters per second squared. So this value right here, whatever it solves out to be, which is the number I had right here, that number right there, the 29.20775, that's the force of kinetic friction. 176.5895, that's the pull in the y direction, and there is your motion. All right, this video was a little bit longer than I intended. I was kind of hoping to do another video, but I'm a little exhausted right now, so we'll see how long it takes to get the other video out. But we'll definitely be able to at least go over them in class. I may try to find another good example that I can do that's not from the worksheets that I think will help explain some of the concepts to everybody. In the meantime, this has been Mr. Diamond. I'm going to put this up today right after I finish it, so hope you've enjoyed your Thanksgiving. Happy Saturday if you see this in time. And I hope to see or hear from you, everybody in class. Have a good weekend, everybody.